Hello everyone and welcome into yet another live stream. A main channel stream. Yes, it is a main channel stream indeed. There we go, that's the link. And first things first actually. Let me write something that will be very important because this already hurts my eyes, which is oh, I don't know how this works. Okay, this is how it works. Gotcha. There we go. I feel like that's a good start. Oh, so much better already. Hi there, Lycan. Hi there, Remco. Hi, this is Napoli. Hi. Hi there, everyone. Hi and welcome. Hi and welcome. Welcome to a live stream about jiggling atoms with magnets. Yes. Professionally. Yeah, it's not a hobby. It's for the betterment of humanity as a whole. Just that all matter drawing of flame. It is a really good drawing, isn't it? The fire cup. I like it. You know what? Keep it in the middle. We're gonna end this size. We're gonna go around it. Yes, jiggling physics. No, actually, well, physics. Blurs the line. Doesn't matter. Yeah, today we will be. I should mention one thing, which is it is unlike the streams with Remco. In this case, I have no clue about NMR. When it comes to NMR, by the way, is the name, I suppose. Up Flames volume. Oh well, see, I knew. Remember when I said that there are some things I'll probably forget about? Yeah. Unlike with the Remco Flames, in this case, I have no idea what this will be about. I know nothing about NMR. Absolutely nothing. So.
You know a bit because you know EPR. As I've discovered, EPR is very different to NMR.
That's not helpful. That is very much not helpful. Where do we begin?
We begin with what you know.
Okay.
This whole stream is going to be me making you feel stupid and you making me feel stupid. Because you're going to ask me questions I don't know the answers to, and I'm going to be telling you things.
Can we just go with the smart one? Alright, fine. Well, I know EPR. I know that one.
Yeah.
I know when it comes to nuclear magnetic resonance, I know what each of the words mean. And I know that if the principle stands the same way, then it's about... Well, if I had to guess, then it would be about somehow increasing the difference between possible energy states of a nuclei to the point where if it goes between the two possible, well, I don't know if it will be two, but when it goes between the energy states, excites or de-excites, then we can detect that and measure at what point happened to measure what is the difference between the energy of the possible energy states.
Yeah.
That was not coherent at all, what I just said.
Okay. They're just as correct. I will say that today, we're basically not going to do any quantum mechanics. So no energy level stuff. Which I know it sounds insane coming from me.
That's the only thing
no energy levels.
Okay, well that throws me off because in that case I don't even want to say that's all I know. That's all I guessed.
Mm-hmm.
So I think that's the end of my knowledge. Where do we go from here?
I'm gonna ask, do you know much about sound physics? Like music physics?
Well, only enough to make conversation. I've never. Well, I know. I have on a couple of occasions seen some physics relating to. Funny enough, before this, I was working on a chapter for a video which included an example which was with phonons. So,
Okay.
but I wouldn't say much. I don't know much.
Do you know what a Fourier transform is?
I think I might, yeah.
Okay. The Fourier transform is like all of NMR. So we Fourier transform everything in NMR.
Please let that not be hyperbole. That will be...
It's not like literally every NMR experiment, every spectrum is the result of a Fourier transform. So it's usually call it Fourier transform NMR if you do the full name.
Okay, that's really good then. Fancy F, I'm relatively confident with that.
So I'm gonna give you an analogy to what we're doing, which is the way NMR works is kind of like smacking a bunch of tuning forks and then listening to the frequencies they produce. Does this mean anything?
I think so. Okay, it's magnetic resonance. I mean, okay, resonance part. That doesn't make
Resonance.
like
Resonance.
like yeah. So far, yeah. Okay, this makes sense. The tuning forks.
Yeah. Okay. I'm gonna start drawing vectors because we love vectors. So you know what spin is, surely?
I was about to say
you vaguely know what spin is.
I do vaguely. Vaguely is doing a lot of heavy lifting
Okay.
there, but yes.
Can you draw? Can you draw? Let me think. We can do a bit of energy levels for this. Spins in no field and then spins in a magnetic field.
No.
Okay. You know EPR, you know the whole like we transition from one state to the other one?
Yes.
What are the two states?
Well, up spin, down spin, right?
Yes. But why is that only possible in a magnetic field?
Well, it's because without the magnetic field, they're both on the same level, but with a magnetic field, they diverge, right?
Yes. I don't like this diagram because this suggests paired electrons, and the whole point is it's an unpaired electron.
Oh yeah, okay, fair. Right.
But yes, yeah. Okay.
Is make it taking an exam or something with no prep. Yeah, that's basically what's happening.
Okay, so we have two energy levels. We have our we're gonna say our magnetic field is pointing upwards, and we call this E0. B is what we use for magnetic fields for some reason. Okay, we have spin up, and we have spin down. And is this logical to you that spin up is the lower energy and spin down is the higher energy?
No, but that doesn't really upset me. I don't have the mental capacity to. It's spin. I just
okay. Imagine your electron or your nucleus. I mean, it's nuclear magnetic resonance. Imagine your nucleus is a bar magnet.
Mm-hmm.
The magnet wants to be pointing the same direction as the field that it's in, right?
Right.
So if you start pointing it the other way, it's not very happy. It wants to go back. Yeah?
Mm-hmm.
And this represented as energy is this.
Oh,
as in,
okay,
if
that
it's
makes sense.
pointing with the field, it's lower in energy because it's happier. It's more stable.
That makes sense then.
And if you let go of it, it would eventually point upwards.
Right.
Yeah.
Mm-hmm.
Okay. So we have two energy levels. Now, if we had just one nucleus, there would be some probability that it's here, some probability that it's here. As we know from statistical thermodynamics, when you have a bunch of nuclei or a bunch of samples or whatever, they populate these energy levels with some kind of distribution. Yeah.
Mm-hmm.
can you maybe draw like dots on these or something? How populated these levels are in a field? Just very vaguely.
In a field,
just draw dots to represent the population of each level.
This?
Okay, this is decent. In NMR, basically our field, even though our field is massive, the population difference is something like, let's say we have, I don't know, 5 million in this one.
Mm-hmm.
This is...
Okay, so I was a bit off. I mean, I got it right that that one would have less.
So our population difference is actually really, really tiny, which is why we need a big field to make it somewhat noticeable. And so you look at that and you're like, well, how do you even measure anything? But the point is, if we start drawing these as vectors, so let's say we've got a bunch of nuclei. We'll say a bunch of them are pointing down, whatever. A bunch of them are pointing up. But slightly more of them are pointing up than down. So we have a net vector.
Net value will still be a very reasonable
pointing
vector.
up.
Yeah.
Yeah? Is this reasonable to you?
Yes.
Okay.
So far, I believe. There's one question I have. Because
yes.
I don't know if I understand it for the right reason, why this one would have less than this one. Because I guesstimated. I think I knew. I don't know if I knew it for the right reason. That the top one would have less, but considering how small the difference is between them, I am no longer sure if I'm correct on why.
What was your guess on why?
It's because we weren't doing it at absolute zero.
This is correct. If we were at absolute zero, then all of them would be in the lower one. Yeah.
Yeah, but because on infinite energy it would be equal. At infinite temperature.
Yes.
So if it's really...
So when I do this, when I say these values, this is room temperature.
Okay. Oh, okay. So it is for the right reason. Never mind then.
That makes sense. Yeah, I should have clarified this. That is a good point. And this is why we do low temperature NMR. Because it enhances this population difference.
You want so as high of a field, as low as of a temperature makes the difference bigger.
Yeah.
More visible and bigger.
So the field doesn't. I don't think the field actually affects the population difference.
More,
the field
more visible,
just
more visible, and that's why I switched to more visible and bigger. The field would make this effect more pronounced, right?
Mm-hmm.
Okay.
Yep. I'm gonna be really mean and ask.
Oh, no.
Can you draw where something points if it has spin? So we say spin up and spin down, but they're not actually pointing directly up or down. Do you know which way they're pointing?
You mean like a spin like this?
No, I mean electron spin.
Oh yeah.
Spin.
So do you mean this?
Yes.
Jeez, I'm not having fun. I'm really not having fun.
Can you expand this drawing in some way? There's an extra thing you should add to this drawing.
I mean, I don't know if this is what you're talking about. Because on the vectors lying the same magnitude.
This isn't what I'm talking about, but this is correct in a way.
I am so not having fun. Okay. Like, doing it blind is one thing, but man, this is spin. Oh, it's been 40 minutes. It's just been spin. Right. Yes. Let's. Okay, I'll be honest. I will not be able to guess what you want me to do in this case. I think.
I'm gonna draw this and this.
Oh. Okay.
Do you remember this?
Yes, I do remember this. as a sphere.
So our arrows lie at like any point. These.
Yeah, and
right?
we sum them together. Yes.
Yep. I had a crisis a few weeks ago because apparently this image is only valid for when you're measuring the spins and not not when they're actually just existing. But we're not going to worry about that for now because that's too quantum.
Yeah, obviously.
Yeah. But so we have this image, but the key takeaway from this is that our net vector is still just an up arrow because these. So if we were to draw axes on this,
so
we would have like
this
z, x, y, whatever.
This gives us this.
Yeah. So they all cancel out in the x and the y direction, and because we're in a big field, there is a net pointing upwards. Very slightly.
So far that makes sense.
So we have a few more pointing in these directions than in these directions. Therefore, as they all kind of average and cancel out, our net vector is this up arrow.
Yeah. Okay.
Yeah?
So far, well, I mean, I don't, never mind. I don't want to say it makes sense. So far, I'm following you.
Okay. Now...
The gasp was making me
how do we talk about this?
This is terrifying. Okay.
Have you heard of llama precession?
Absolutely not.
Llama is spelled Laromor. Wait.
Oh.
Larmor.
Llama.
Let me just type it in chat.
Llama. Absolutely not.
Have you heard of a llama frequency?
No, nothing llama related.
Okay. Okay. I'm gonna just spit a fact at you that you're gonna have to take as a fact because I haven't looked at the physics yet. Which is that when you have so think of a gyroscope, right?
Yeah.
There's something spinning, like a gyroscope. Do you know how it precesses?
In what way? How it processes?
Like, so when you have a gyroscope precessing, or a gyroscope spinning, it's spinning along its axis, but it will actually precess around on like a second axis.
So you mean like if I have a gyroscope that's spinning like this, then the entire gyroscope will spin like this. Is that what you mean? I don't know if my drawing.
Kind of.
My goodness, drawing three-dimensional spin on a flat surface is brilliant.
So we have a gyroscope that we'll say is spinning. It's spinning on its axis like this. So the gyroscope is spinning, but if you've ever held a gyroscope, it actually, while it's doing this, it also very slowly does this. So we're saying this point is fixed, and it's very slowly kind of tilts around this ring.
Yes.
Have you seen this before?
Yes, I have. I do believe.
Okay.
Go on.
Sorry. I thought you were gonna say I do believe something.
I believe.
You do believe.
I was going. I changed my mind, but do go
on. Basically, spins do the same thing. So spins will precess when they're in a magnetic field. And so what this means is that if you have a spin, so say one of these arrows is one nucleus, the nucleus is precessing along this yellow circle.
It's mental because you say, okay, in this, okay, wait, no, we're talking about the nucleus. Quick question.
Yeah.
Please let that be the case. Because nuclei are big, relatively. Can we model nuclei as spheres, not points? Is it actually spinning, or is it still spin?
It's spin. This is the property spin.
Still.
No, we can't model it as a ball. I mean, you could probably model it as a ball spinning and it would still work most of the time. But this is the spin property.
Okay, right, because in that case, you do realize that when you say it's also spinning along the, like, the it in the sentence, it's still spinning. The it is really, I need to like live in active denial of that. my brain always asking a question, what if spinning? No, not the right question to ask. Just accept. Okay, yeah, so that makes sense.
I mean, this is the conundrum that scientists have had for years, right? Which is that they behave like they're spinning, but it's just an intrinsic property. And so for this discussion, we're going to talk about them like they're spinning, because they behave like they're spinning.
Right, all right. So it's rotating also around another axis because of this kind of spin.
Yeah, and this axis that they're rotating around is, I should draw it with red, is our magnetic field. This, right?
Yep.
Yeah. Okay. So, this as they process, this property that they have called the llama frequency is quite literally the speed they process at. So this is a property that they have that is different for different nuclei, and I don't quite know where it actually comes from. It's to do with like the gyromagnetic ratio of things. That also doesn't mean anything.
But question, how does this procession affect it? Because the net will always be either directly up or directly down, correct?
Yeah.
So how will that kind of procession affect it? If you
will find out.
Oh no. Because in my head, if you have a vector 0, 0, 1 and you rotate it on the 0, 0, 1 axis, then it doesn't matter how much it rotates; it will still just be 0, 0, 1.
Yeah.
Oh no. Okay, fine. Yeah, let's carry on. All right. Thank you.
Yeah.
Okay.
Yeah, you're right. Then this net vector isn't affected by the spinning for now. It will be.
Okay, yeah.
but for right now, it's not.
I'm so silly of me to ask. Carry on.
But yeah, if this net vector is only pointing up, then it doesn't matter what the x and the y directions are doing.
Okay.
The point is that in NMR we force it to do stuff with the x and the y directions.
Oh, okay, that makes sense. All right, and genuine, not even ironically, that just genuinely makes sense. That's good.
Yeah. Let me just think through what I'm going to say next, so I get it in the right order.
Llama freaking or llama? I'm lost. Oh, don't worry, Italian mapper. That is the point. Is Flame being paid to be a tutor? I mean, if Flame actually manages to make me understand spin through this process, then if you manage, I should pay you in that case. That's not even as tutor. I would just be that impressed.
I mean, anytime I talk about spin, I'm just giving facts about spin and then telling you how they apply to like chemistry.
I've noticed.
Because if I wanted to understand spin, I would be a physicist, and I still wouldn't understand spin. So. I'm just double checking something before I say things.
I can explain spin poorly. I mean, if you think about it, I do have to say, it is. I do understand the merit of the spin because it is just ridiculously convenient how closely it behaves with spin. It is mad that you can model it as spin and it fit in this perfectly. So I do understand why. It's just that. Well, you all have eyes. You're seeing what I'm saying.
Well, it's because it's a type of what's it called? Angular momentum. And it's the reason that like electrons do everything they do. So it's like if they didn't do this, then we would be a bit cooked.
This is just...
Yeah. I'm just checking something really quick.
Yeah, I'm just reviewing everything we've noted down.
Okay.
If you're just tuning into the live stream, why? Yeah, okay, but so far it hasn't been too bad. I do jest,
okay.
I do josh around, but so far it hasn't been too bad. I'm so ready for it to get so much worse.
I'm going to draw vaguely what the NMR setup is like. Yep. We're not going to bother with solid state NMR with magic angle spinning. That's for another stream. And it's called magic angle scientifically.
Yeah, just like good numbers, magic angle. It's no standard practice.
Yeah. So our sample sits, somewhere inside a massive magnet with a field pointing this way. Yeah.
Yep.
Inside this magnet, we have a probe, which we kind of just stick. We stick this inside. This is what I was carrying home today. And this probe has some features. Is the coil in? Okay, there's a couple coils. One of these coils is wrapped around our sample, so it's like this. I guess let's join this up. This is a coil wrapped around the sample. And another coil, I think, is just perpendicular to the sample. So the red one here is our detector coil. And blue one is our emitter coil. And the way this blue coil works is it produces an oscillating magnetic field. So it produces a field along this axis, as you can imagine, because it's a coil. And the field is going that way and that way. So far, so good. Yeah?
So far, so good, yes.
So it's oscillating. So it goes a bit that way and then back and then back and then back. We call it nuclear magnetic resonance because the frequency that this oscillates, when it matches the Lama frequency of the nucleus, it will actually make our magnetization vector tip sideways. And it can, if you keep applying it, it would kind of just spin all the way around.
I think I see it. Is it? I mean, okay, do I see it? I think I see it. I know for the right reason, because basically, if it matches the Lama frequency, then okay. So, am I understanding this correctly? We have our net arrow, right? We apply a sideways magnetic field, so we tip the arrow a bit from directly on the z-axis. Is that right?
No.
Damn it! I thought I had it.
But this is a good starting point, and this is what I thought before I.
Yeah, because then it would make sense, because then if it would match up with the Lama frequency, then it would effectively mean that we're tipping the arrow the same way on the same cycle of rotation, which would in my head would just amplify it instead of cancelling it out.
That's actually correct. Yeah, that's yeah.
Okay. So I just got
in terms of what you said about the Lama frequency makes sense.
Yeah, because I mean
basically we can't just imagine that it's like this. But yeah, this is correct. Yeah. We're gonna break down how this oscillating field in one direction, in one axis, produces effectively what makes this arrow tip sideways. And the thing is, when we tip it, so say it starts here and it ends up pointing this way, Now, because it has an X and a Y component, now it processes, right? Now it starts twisting around. And so, but because it's still in the field, it returns back to here eventually. So you might have seen this diagram where it kind of does this, and it and it returns to the top. So it does this like weird spiral pattern and gets to the top. We're gonna break this down.
Yeah.
So I need more space. Let's go to the top. So we have you heard of the rotating frame?
I can't say I have.
Okay. The rotating frame is as if, so we're looking at the nucleus. Suddenly we start looking at it, but we're spinning with the nucleus. So say we have some
frame of reference.
It's a frame of reference.
That makes sense. The name makes sense. Okay.
Yeah. So it's like the stationary frame is as if you're standing looking at a carousel, and then the rotating frame is as if you get on the carousel and you're looking at the stuff inside it. Like it stops moving because you're in the rotating frame.
That does make sense. Yeah.
We have an oscillating magnetic field, so I'm going to draw a diagram. It's never been drawn like this before, but I'm going to draw it like this. This is time. I should probably draw my T a bit better. And we have an oscillating magnetic field that points, we're going to say, points this way, and then a bit this way.
Sine wave.
And then it's in the middle. Yeah, it's a sine wave. And I'll do a whole cycle. Okay. Are you happy that this is the same thing as saying we have a field that's oscillating in these two directions?
Yes. Really happy. Yeah. I love me time graphs.
Okay. What we're going to do is we're going to do something fancy and say, first we're going to say that the frequency of this, I actually need to draw straight lines better. The frequency of this is our llama frequency, which we draw with lambda. So this frequency is at the llama frequency. We're just going to say this for now. And then what we're going to say, what we're going to do is we're going to break this down into two component vectors. And so that this is the way we rationalize the fact that this oscillation makes our nucleus tip. So we're going to break this down into two component vectors. We're going to draw, let's draw. One of them is like this, and I'll draw a purple one like this. So that they're both pointing at in the same direction initially. Then we're going to say they start to go a bit diagonal, but they're going in opposite directions, right?
Oh my goodness! That's clever.
And then here, one is pointing up, and the other's pointing down.
Do they keep their magnitude throughout?
They do. Yeah. Sorry, I'm drawing this really badly.
No. It's fine. It's.
And then here, one is pointing that way.
It's really clever. Because effectively, what this is just. Also, I have another question, but I suppose it's going to be answered by a drawing, so I'm just going to.
Yeah, you can ask.
Do they rotate, or do they do rotate? Okay, there we go. Yeah.
Sorry, this is taking ages.
No, it's fine.
Because I'm doing two colors.
Effectively, just the Euler's should be E I theta plus E minus I theta. I don't know if I'm getting the maths right.
I actually have no idea what you're talking about. Maybe.
Just I don't know. For some reason I was thinking of it on the complex plane. Yeah. Okay, but this makes sense. This makes a lot of sense as well. And
this is drawn so badly that the like center's way off and everything.
I don't mean to imply that this is a cult, but you, and I'm saying collectively, you as the physical chemists that deal with this, you have managed to somehow find a way to turn the one thing that isn't spin in spin back into spin. What's more, two spins actually. It's impressive because it's two spins.
I mean, it's because of precession, which is because of spin. So it is still spin.
But right, so right now,
so our purple arrow is going
single axis that they're going through.
Yeah. So if we're saying that this is the X direction, then this is the Y direction, and this is the Z direction. Yeah. So they're rotating in the X and Y plane.
I genuinely don't know where this is going, but I already think it's so clever to break it down into two. Because for some reason, just having two vectors with the same constant magnitude throughout feels more elegant, and I don't even know where this is going.
Okay. Let me just rub. Oh, I thought that was a background. Okay. I can't break the illusion. How do I can't highlight this because it. Okay. Can I delete it? Delete. And delete this and this. And...
Hold on.
Let me click it. Okay. I swear there was a way to change the background instead of just putting a black image there.
There was. I just don't remember how I did that. So
settings, background, dark. There we go. Now I'm gonna delete your black image, and now we have a dark background.
Yeah, beautiful. Okay. We're professionals. I just like.
Okay.
We're professional jiggling atoms. Yeah.
So now we're gonna hop onto the carousel. And look at what these look like when the carousel is spinning at the llama frequency. Okay.
Okay.
So, for one, so this is stationary frame. Probably should just use the text. Stationary frame. Now we're going to hop into the rotating frame. So, in the rotating frame, for one, I'll draw our green arrows as a frame of reference.
I imagine the green arrows will now be not only shrinking, growing, but also rotating.
Yeah.
And if I don't know, should I talk over as you're drawing, because I don't know if, because I imagine.
Yeah, you can. Yeah.
So I imagine green arrow will just be rotating and shrinking, growing, whilst if we're hopping onto the blue arrow, then the purple one will rotate twice as fast.
Yes. Yes, exactly. Wait, can you repeat? Wait, can you repeat the beginning of that actually?
The green arrow will be oscillating and rotating at the same time. And if we hop on the blue arrow, then the purple one will rotate twice as fast. If we hop on the purple arrow, then the blue one will rotate twice as fast.
Yes. And what does it mean to hop on the purple arrow or hop on the blue arrow?
Well, it means that we're just looking at it from the perspective of that arrow. So it's kind of like...
Actually, I'm going to stop drawing this green one because it's confusing me.
I'm not... Oh, jeez, I don't know how to describe it in the proper way. Well, basically, I imagine it's like... just relative frame of reference.
Yeah.
So we freeze... from our perspective, we freeze the arrow, but we do that by moving in the same exact way as it moves.
Yes. So you basically figured out what I was about to draw, which is very intelligent of you. So this frame, should we hop on the blue or the green arrow?
I think the blue one. For some reason,
like the blue one?
I don't know why, but for some reason it feels right.
There is a correct one, but I don't know. I always forget which way is which. Rotating, and we're rotating this way in our frame. So, as you've identified, obviously they both start pointing this way.
Oh, I do have to say, diagram-wise, it's such an elegant diagram. I'm enjoying it so much. I was on the very beginning. I was confused why you were drawing the arrow instead of drawing it as a graph, like connecting them, just drawing a sine wave. But it makes perfect sense. It is very. My OCD is very pleased.
I'm still gonna draw all of them.
I'm just thinking of trying to guess where it goes next. Because if we break it out, go vectors like this. Would mean twice as fast.
Okay, so we see one of them is constant and the other one is going twice as fast the other way. Yeah.
Yep.
Okay. Basically, this is resonance. So the point is that there is a specific frequency at which suddenly one of these components becomes constant in the rotating frame. And this frequency depends on what this frequency is, right?
Hold on, wouldn't work at any frequency.
It doesn't work at any frequency because here what we've said is we said our rotating frame is at the lambda frequency.
Oh, okay. Our frame is at lambda frequency, not the arrow.
Yeah.
Okay.
So if
that makes sense.
If we were rotating at a different speed to this,
then this arrow
it wouldn't match
rotate.
up, right?
Yeah, that makes sense.
Yeah. But you're right, it would slowly rotate if it was like a close frequency. If it was way off, then it would just be nonsense. But if it's a close frequency, then the blue would like slowly rotate in one direction or the other. And if it's bang on, then the blue is constant in one direction.
Also, would it work for multiples as well? Like n lambda?
What do you mean?
Well,
as in like double the frequency?
Yes.
That's a good question. I don't think so. I mean, my answer is no, because otherwise I would have heard about it. But I'm trying to think of why. It could just be that if you have like a multiple, then you end up with the blue doing this. And so it's effectively oscillating. Therefore, it cancels out. It might just be that.
Yeah, but then in that case, what about half lambda, right? Because in half lambda should have opposite effect.
But then you might get... let me think.
I mean, because both, I think it has to do with the second arrow then. Because if it's twice, it rotates twice. This rotates, no, this also rotates.
Second arrow is going the opposite direction though. I get what you're saying. I think the result is that there will be some kind of cancellation if you try and do double or half. Because yes, at some points the blues would still match up, but at every other point they would be not matching up in the exact opposite way.
Oh yeah, okay, that makes
even
sense.
if you do half.
Yeah, I'm just thinking.
I think, yeah. Because we can't control like which time periods we allow this for. We have to just do it for constant time.
That case,
so this is a constant effect.
We would get this, and if we flip it, then but then if we
okay, let's say our speed is.
Let's move
on.
If
we're taking just this one and this one and this one, this is effectively what you're saying, right?
Yeah, but then the question is like you can go either way, right? You can either do 2 lambda or you can do half lambda. And
I think the point is that even if we're doing this, we're still taking the ones in between. I don't know.
Yeah, let's move on from this. It doesn't matter.
Okay.
Yeah.
Okay, so we have And this is still in the rotating frame. We have 3 axes, X, Y, Z. And we're saying that the result of this is that we get a continuous field in this direction and a wildly spinning one, whatever, doing this thing. Basically, the spinning one we can just ignore, which sounds like cheating, but the main point is that because this one is matching up, I should be using it. Because this one is matching up, it just massively amplifies its effect. So it becomes a strong effect
wild.
Because it resonates.
That is wild.
This is resonance, right?
Oh.
And so we are going to call this B1. And so we have 2 fields. We have this, and this is our B0.
So effectively, with this one weird trick, you've turned a resonating magnetic field into a constant magnetic field. Physicists hate them, you won't believe number 7.
Yes.
So
it's literally you just hop in the rotating frame and this oscillating field becomes a constant field.
It feels like a magic trick, to be honest. Because like I've seen all the steps, but the beginning and the end don't make sense.
So I was very confused by this because basically most of the books I read went from this to directly to this, and they left this out, and I was like, how the hell do you go from an oscillating field to a spinning field? Because this is spinning in the stationary frame, right? Like if this is stationary, then our B0 is spinning around at the llama frequency, yeah. B1, sorry. So I was like, how the hell did they do this? And it took a while to eventually find something that explained that we break this down into component vectors and then just ignore one of them. The reason we can ignore it is that it's just going so fast that it's in all directions, basically. And so it kind of just cancels itself out. Yep.
Okay.
Okay. Yeah.
I mean, okay,
that's all I'm going to say about that for now. Yeah. So another effect of this is that I think our B0 becomes a lot smaller than B1. So I think the B1 is quite big because it's resonating.
Quick question.
Yeah.
B1 is still from our green coil. Not blue coil, right here at the bottom. Right? Like
yes, there is no red coil activity here yet.
Okay, so B1 is that. Okay, this is the part where I'm saying it's like a magic trick, because effectively you have an oscillating, like you have a field to time, right? You have this, and then you say, okay, let's look at it different, and we end up with this, and like, what happened?
Yeah.
This is, I can't understand.
Yeah. But the point is that we're
just looking at it different.
Our nucleus rotates at this same frequency, processes at that same frequency.
It still feels like a magic trick.
So it doesn't work if our nucleus is at this frequency, right? Like it has to be at this specific frequency.
Okay.
And the reason, one question you might ask, which is related to what you asked before, which is if we come back down here, do you remember when you pointed at this, our up vector, and you said, why does the precession matter if it's only pointing up? What happened? Why is the screen white? Oh, I'm reconnecting.
Okay, so now it makes sense, because if there's a constant field going sideways, then I imagine, if I had to make a guess, if we have B0, hold on, that's it, no, B0, and if we also have a B1, then I imagine what we would care about is a B total. Oh, no,
not really, no. We actually only care about B1 now, for now, because B1 is much bigger than B0.
Okay. Well,
because B1 resonates, it's much bigger than B0.
Even simpler, actually.
Okay, let's come back up here. So So I'm gonna draw. Red is our spin. Not our spin, our magnetization. So the difference is that spin is a property of one nucleus, and magnetization is the net sum. So we talked about the net sum. Magnetization is the net sum of all the nuclei. Yeah.
Yep.
We only need to talk about magnetization for this next bit, because it still behaves like spin, which is, say it's pointing upwards, and then we apply this B1 field. What happens to it when we apply this field? And you're gonna give the wrong answer, but I'm asking you anyway.
Could you repeat again?
Okay, so we have this net magnetization, which is pointing upwards.
Yes.
What happens to this magnetization when we apply a field in this direction?
Okay, so you said I'm gonna give the wrong answer, which means it definitely won't be the obvious, which is it'll shift towards this. But I'm guessing the reason why it won't shift towards there is because there is still this going on. So I'm guessing that if you my whiteboard just went pure white. Oh. I was about to make my grand reveal. Oh, Discord. Living Tombstone reference.
I mean, actually, you don't. Yeah, sorry. Continue. Yeah.
Not filling me with confidence.
No, it's the thing you said. I'm not sure if it's true, but I need to think about it.
I was gonna guess that.
One of the things you said. Like, you can keep going.
It will go in like a spiral until it starts oscillating.
No.
Damn it.
Can you remove the yellow as well? It doesn't like.
Oh wait, will it be? I don't think I can remove the yellow anymore because I disconnected there we go. Will it go this way?
Yes.
That makes sense.
Why?
It will go this way because it's being pushed. Well, it would still be the yellow, right? It would still be because of this rotation.
No.
No, that's not good because that's genuinely what I thought was the reason.
But it does go to the green arrow. Okay.
Oh my! Basically, there was this one video I've watched about spin years ago, and I remember from that video that this exact thing happened, with a gyroscope.
With a gyroscope.
But I really thought it was. Wait.
Was it that Veritasium video?
Yeah, I think so. No, not Veritasium. I think it was Vsauce actually.
Oh. I remember the Veritasium. They had a Veritasium video about like bike wheels with gyroscopes.
No, because we don't care about them anymore. No, in my head I cannot get past the large round yellow arrow.
Okay, I'm gonna draw a different large round yellow arrow.
Yeah.
Which is actually wait, other way around.
This rotation.
This is precession around our B1 field. So when we have a field near magnetization, magnetization precesses around it.
Oh, yeah. I hate magnetism. Yes, that makes sense.
So it precesses around the B1 field.
That makes sense. Yes.
Okay. So what this means is that we apply the B1 field, and this red arrow points here. It will tip that way, and it will. If you keep the B1 field, it will just keep tipping that way, and it will keep going, and it's just going to spin around and around our ZY plane. Yeah.
Mm-hmm. Stamp was right. Yeah.
Because our B1 is in the x-axis. I love vectors. Okay. Does this make sense so far?
It does.
It's very convoluted.
The convolution isn't really what gets me. It's the abstraction, because my brain keeps trying. Like, okay, I've been dealing a lot with arrows in Blender, fortunately. So at least I'm used to arrows in a vacuum just doing their own thing. But my brain keeps, whenever you say anything like that, my brain keeps asking the question of, that is rotating. What is rotating? I keep suppressing it because I know that it doesn't matter. But yeah, it makes it. In this case, so up to this point, this movement completely makes sense. So basically, to like recap so far, we have a nuclei, and then
it's actually I'm sorry, it's nucleus for singular.
Nucleus. Oh, just singular.
Nuclei is plural.
We're dealing with just.
Well, if you say a nucleus, like you're saying a nuclei.
I said a. I'm so sorry. I'm exhausted.
It's alright. It's alright.
So we have a nucleus, and then we apply an oscillating field on it. Then what's going to happen is it's not spin, it was magnetization, right?
Yeah. So magnetization is a bulk property when you have a bunch of nuclei.
So its magnetization will switch from an upspin. Not upspin, jeez. Its magnetization will switch from a purely upgoing vector to one that's revolving around the axis of the oscillating magnetic field.
Are you talking about in the rotating frame or in the stationary frame?
In the rotating frame.
In the rotating frame, yes. Can you draw what it would look like in the stationary frame?
Well, I imagine the stationary frame, B1 would start moving. B1 would just start moving. So if B1 starts moving, then that means this entire rotation would start rotating as well.
Yes, yes.
There's
a lot of arrows, but I know what they mean, yeah.
Yeah, that's...
So where does our magnetization vector go?
Well, our magnetization will go on an absolutely wonderful spiral throughout the sphere.
Yes. Beautiful.
this
is beautiful. This is what we love to see.
It honestly looks as if I just made a mistake and had a mental breakdown. Try to scratch it out. But on its own rotations, yeah, that's good.
Mm-hmm.
Okay.
Okay.
Are we switching from a rotational frame to a stationary frame?
No, I was just asking. I was like checking your understanding. By asking you about the stationary frame.
Okay, that makes sense. I'll just move that one then. Yeah. So I'm with you so far.
You're with me so far. Okay, good. Where was I going next? I want to take a second to convince ourselves that B1 has to actually match the llama frequency. Can you tell me what happens, or show me what happens if B1 doesn't match the llama frequency?
Okay, I'm going
to maybe start tipping it and then see what happens.
Yeah, I was about to say that. I'm going that like if it's at the Z, then llama frequency doesn't matter. Llama frequency doesn't matter. So if we tip it a bit, then it does matter because all of a sudden it starts oscillating this way.
Yep.
So the reason why it matters. Okay, so first, what happens if it matches? Well, if it matches, then the arrow will end up in the exact same like rotational axis on the plane, on the exact same plane.
The ZY plane, yeah.
Yeah, it will end up at the ZY plane at a fixed interval. So that's why the rotation will go this way. If it's not, however, then it would be a bit off. Like it points ZYX somewhere in that quadrant.
Yeah.
And then that's where it will be. And then in that case, if we all of a sudden have a rotation, then that rotation will just that way, and then fights against it. I'm spinning.
We need another rotating frame.
Yeah. Okay. I have I could either go through the process and actually try to imagine.
You don't need to go through the process. I think we can
make a guesstimate, which is that they all effectively. I don't want to say cancel each other out, but like they go in all sorts of directions to the point where it's equivalent to them canceling each other out.
Yeah, it basically just doesn't
You get no net.
do much. It kind of just it kind of will just return to Z, I think.
So the two, okay.
Yeah. Basically, it has to match the B1 in order to do this tipping properly.
Right.
Right? Yeah. Okay. This is resonance, magnetic resonance of the nuclei. This is NMR. This is what we do. Does this make sense?
No,
It took
I
a
mean,
while.
okay,
But...
okay, it makes sense, but like, okay, this makes sense.
This makes I know. Yeah, you might ask, how does this like apply?
My question is, what? I mean, okay. This, first of all, this makes sense is pushing it. Let's just say I am, I am not extremely confused.
Okay.
Because I have so many questions. Because the most logical question I want to ask is, what does this mean? Like, okay, I get what happens to the magnetization right now, but what does it mean for magnetization to go also? So does it mean that it interacts different? I'm going to guess that it means that it interacts differently with fields.
Yes. Kind of, yeah.
Let me think about how.
Are you asking like how we detect it, or what it means in terms of the molecule?
I suppose I'm building up to how we detect everything. Because can I ask about the red coil, or is it too soon?
Yes. That's what I was going to go to immediately.
Guess that it's going vertical, right? The magnetic field. Because
what do you mean?
Well,
okay. So I'll say this red coil, we're not running current through it with the machine. We're not putting current through the red coil.
Is there a difference when it comes to construction of coils? So like, do we? Jeez, no, never mind. That complicates things.
I think we should go back to the top, and then I'll ask you a question about the red coil.
Okay. Yeah.
If you come back up here,
I am bug.
So we have our axes, and we're still in the rotating frame. So we tip our magnetization into. Oops. Cannot draw straight lines. Into the y-axis. Yeah.
Yep.
What happens, or what is happening in the stationary frame while it's in the y-axis here? So I will actually relabel these. This is Z prime and X prime and Y prime, because we say prime for the rotating frames.
Okay, so is it going this way in the rotating frame? But in order to go back to a stationary frame, we need to add this kind of rotation.
You're overcomplicating it. I need to reframe my question. So we've tipped it into the y-axis.
Yeah.
And what we do as the NMR spectroscopist is we say how long we're applying B1 for. We define a certain amount of time. And this time is how long it takes for our arrow to go from here down to here. And then we stop applying B1. So our magnetization is in the y-axis, and then we stopped applying B1. What happens?
Is it pointing? Is it pointing?
Is what pointing that way?
The magnetization.
Why?
Because without our, I think I'm thinking about it the same way again. Like in my head, we just need to. In my head, us going from a stationary to rotational frame of reference meant just subtracting a rotation. And then
so we're still in the rotating frame here, but we can switch to the stationary frame if you want. I'm just asking you what happens in either frame.
Oh, in either frame.
Yeah.
Well, the magnetization is moving. It's no longer. It's different. I don't know. I don't know.
Different how?
Well, it's pointing a different direction and also moving. It's not like it was pointing up. It was static. It was constantly pointing up. Right now, it's not only not pointing up, but also moving to a different direction.
What do you mean? Moving to a different direction. What's making it move in a different direction?
Well, the field we're applying on it, B1.
Okay,
This
we have B1.
Plus the
no, but we have no B1. B1 is the blue one, right?
Yeah.
We're saying that we've stopped applying B1.
Oh, well, if we stopped applying B1...
So what happens when we stop applying B1 and our magnetization is in the y-axis?
Wait a second. Oh, it goes back to Z.
Yes, yeah. It will slowly go back.
Is this the echo?
To... No.
Oh, I get so excited for a
second. It will slowly go back to the z-axis, and eventually we will end up with our arrow pointing up again. My question to you is, what does all of this look like? All of this, what does it look like in the stationary frame?
Well, I don't have a good answer. I have an answer.
Yeah.
Which is that... Blame Remco for this. I've been doing too much physics recently. If we imagine a coordinate that's like the difference from... that's like a magnitude of the difference from our original magnetization to the magnetization that we have currently. So that's post the fact. Then the graph in relation to time of that generalized coordinate would look something like this. Am I making any sense?
I have no idea what you're talking about, I'm not gonna lie.
so like okay, so we have the magnetization before, during, after, right? This is how it progresses. Yeah, so the difference between... So then if I make like shadow arrows of where it would be if we did nothing, right? Then this right here would be the distance between them.
Okay, I see what you're saying, yeah.
So this distance, like the graph, it starts at 0, ends at 0, but goes to up. And I'm guessing that, the reason why I phrased it that way is because I'm guessing that if we wanted to measure in some way, for example, I still don't know, by the way, what we're trying to measure, because I know nothing. But hypothetically, if we were trying to, for example, find the lambda frequency, then if I was in the position where I had to find the lambda frequency, what I would do is I would slowly increase the frequency of the green coil until this happens. Because if we normally have the green coil, if it doesn't match the frequency, then this line would just be flat 0. If it does have the frequency, however, then it would go up and then it would go down. So if there was a way to somehow, for something to happen right here, I don't know if I'm also just projecting EPR into this, because what I'm describing is...
this is you're describing like continuous wave NMR, I guess. Okay, because EPR is like you're sweeping the field.
Yeah, but I mean, but you get what I mean, like the
EPR
I get what
you're saying.
Where like you're
seeing
you
when
wait till
when this happens. Yeah,
you wait till it crosses. So this is kind of... Yes, that's the answer to the question.
Okay. Basically, no. Basically, just no. But it is a good concept that is grounded in scientific principles. It does not come from nowhere.
C-.
So. I'm going to ask you a simple question, which is, let's say we have an arrow pointing. So I'm gonna take this and I'm gonna say, let's say we have an arrow pointing in this direction in the rotating frame. What does this look like in in the rotating frame? What does this look like in the stationary frame?
This.
Why?
Well, it's because at this point, like if we go back to the graph, in order for it to be rotated 90 degrees, it is this point right here. And at this point right here, there is a 90-degree difference between our rotational frame and our stationary frame.
I don't get what you mean.
Well, okay, so
you mean they're like out of phase by this amount of time that it takes for them to rotate 90 degrees?
No, I mean that this is like all of this is the same thing, except this is in a rotational frame, this is in a stationary. So if we have our arrow, the red one, if we have it pointing sideways right here, right?
I'm saying this has nothing to do with B1. This has nothing to do with any of this this field. So I'm saying all we have no fields. All we have is this one red arrow, and in the rotating frame at the llama frequency, this red arrow is.
I think I'm misunderstanding something.
Mm-hmm.
Because okay, so here's the thing. Let's imagine a ghost B1. So this is not a B1, only where B1 would be, right? So I don't know, B01, whatever. It's not a B1, but it's where it would be.
Did I lag out or did you lag out?
Did I lag out? Oh no.
Oh, okay. You lagged for a second.
Okay.
Yeah.
So let's say that this is a B01. So this is where B1 would be. It's not the product, it just would be there. Mm-hmm. If that's where it is in our rotational frame, then in our stationary frame, it would be rotated by 90 degrees.
I don't get what you mean by this, by saying it's rotated by 90 degrees in the stationary frame.
Well, it's because our frame of reference is rotated 90 degrees the other way.
No, our frame of reference is rotating. It's not rotated, yeah, I know, but it's rotating. Up to
this point...
Yeah, okay, yeah. If you pick a certain point in time at some phase difference, then yes.
So like at this point right here, the difference between our rotational frame or our stationary frame is 90 degrees.
Okay, I get what you mean. Okay.
Yes.
This isn't what I'm asking though. I'm not asking for a snapshot of the stationary frame. I'm asking for what does an outside observer just see?
Not in that point, only from that point on.
What do you mean?
Are you asking me about this?
Okay, I'm saying we don't worry about points in time. We're saying so all of this has been standing on the carousel.
Mm-hmm.
What do we see once we hop off the carousel and go into some stationary frame?
Oh, so this entire process.
Yeah, the whole thing. So for one, we would see the carousel spinning, right?
I imagine spiral.
Yes. Where's the spiral? Can you draw the spiral?
Well, the spiral would be if we red. Hold on. The spiral would be like this. Spiral.
Is this for this section going from here to here?
Yes.
Like tilting.
And,
yes.
And then it will just go back.
Yes.
Okay, so expanding and then shrinking spiral around the z-axis.
It's not expanding just around the z-axis though. It's like it's tilting into the xy, right? Like at this point, it's purely in the x and the y planes, and then it tips back into the z-axis. Yeah.
Mm-hmm.
Okay. Do you remember at the start when I drew something like this and I said this? Do you remember, like, right at the very beginning of the stream?
Yeah, vaguely. So
This is what you've just drawn. This is what you've just drawn. You've drawn the thing I foreshadowed at the beginning.
This was a journey.
Yeah. So, my question to you is, what happens when I think what happens when we have this spinning in this direction, so spinning around like this, and we have a red coil around it like this. So there's a coil here, and our magnetization vector is spinning this way.
It charges a coil.
Yes.
Oh my goodness. Yeah, so that's how you detect when.
So what we're detecting is the precession.
So
right?
Yes, that's how we know when the llama frequency matches the frequency of the magnetic field.
Yeah.
Oh.
Yeah.
Golly.
so what we're measuring is the precession.
Wow. That was a journey.
Now, I will say...
Hold on, what's the big magnet for? Because...
The big magnet is to give us this red arrow in the first place. Because if we don't have the big magnet, there is no net magnetization.
That is
and so we can't do any of this.
That's
None
hilarious.
of this works.
That is hilarious. That is genuinely hilarious. Because whenever you send pictures of those massive magnets, they're not even there for the experiment. I mean, they are there for the experiment, but they're not like...
It creates the conditions for the experiment, yeah.
They're equivalent to... Not equivalent, but they serve the same function as cooling it.
Yeah, I mean, cooling it doesn't do anything unless there's a field, right?
Yeah. But yeah, the reason why
if there's no field, then the two levels are degenerate. Yeah, they're the same energy.
The reason why they're big, that's
so when you look at the whole instrument, this massive chunk of whatever,
and
there's nothing. The whole thing is just a big magnet, and then all of this happens with the probe. The probe is what does this, which is the thing I was bringing home today.
You were effectively bringing the entire experiment.
Yeah.
My goodness. The entire time as you were talking about the probes, I wasn't asking what they do, because the entire time we had the contract that I was supposed to wait for the stream. So I had no idea up to this point what the probes were doing.
So I will say, you were saying that it's like we're messing around with it until the two frequencies match, right? Like the llama frequency and the changing magnetic field.
I have already a note to that, which is I have a guess why this wouldn't be easy, or it wouldn't work. Which is that when it comes to this, you need a certain amount of time for this to happen. So it's not like as if you can just like when you have a graph of the frequency, I don't know what, theta, why not, frequency to time, then it would need to be like this.
Where are you? Oh, over here.
It would need to be like this, and then the delta theta, if it's too small, then the experiment would take ages. If it's too large, you might miss it. Am I in the right neighborhood?
Yeah. Kind of. So you remember up here when I was like, we apply B1 for a certain amount of time. The amount of time is the amount of time it takes for our magnetization to go from the z-axis to the y-axis.
It's comically short, isn't it?
This is like microseconds.
That's surprisingly
is it
long,
microseconds?
actually. That's surprising.
It is long, but it's because it processes around B1. And then actually this relaxation time to go from here back to here varies wildly and can be microseconds, or it can be hours.
That's
Like it can be
mental.
anywhere between microseconds and hours.
I mean, first of all, microseconds is already an absurdly long time for something on the scale of a nucleus.
Sometimes days, actually.
That is mental. I have no other. Wait, do you need the entire relaxation time in order for? Hold on.
That's a good question. The answer is yes if you want to. It depends on what you want to measure. Yes, if you want to be measuring things very quantitatively, and no if you just want a lot of signal efficiently.
Okay, so I imagine it's more like. Wait, first of all, first question before we get there, because I kind of said I haven't cleared up. Is part of the experiment like finding these frequencies?
Actually, no.
Okay.
Kind of, but no. So basically, different nuclei have very, very different llama frequencies.
That makes sense.
Wildly different. To put it into context, when someone says an NMR magnet is 400 megahertz, what they actually mean is it's a 20 Tesla. Is it 20? It's like 15. It's like a 15 or whatever Tesla magnet that pushes the proton resonance frequency to 400 megahertz. And at 400 megahertz proton frequency, the same, if you put carbon in the same magnet, that's 100 megahertz. These very, proton to carbon is a factor of 4. And the difference between them will depend on that factor and also the field you're putting them in. So it's like the gyromagnetic ratio times the field will give you the llama frequency.
Right. And wait, and so even with 400 megahertz, it's still 100 megahertz.
Wait, I'm saying you have a certain magnet that's 15 Tesla, and protons in that magnet are at 400 megahertz, and carbons in that magnet are at 100 megahertz. And then every other nucleus has its own specific frequency that it's at.
Okay, that makes sense.
And so when we do the experiment, we already know that protons are at 400 megahertz. So there's we're really running out of space. There's some range of frequencies of llama frequencies, and maybe proton is here. So we'll say 1H. I say proton. I mean hydrogen 1, the isotope, and we'll say carbon 13 is like here. And when we do NMR, we tune to one of these frequencies. So we say, okay, we're gonna do our pulse at 400 megahertz, and then what we actually measure is we essentially zoom in on this, and we look at this range, which is a very small snippet of potential llama frequencies, and in here we will have very, very slightly different frequencies for the different protons in our molecule. So we pulse a range which is quite small, and within that range we can excite multiple frequencies. So the way this works is, as long as our B0, our B1 is at a close enough frequency to the nucleus, it will still resonate.
I don't know if I'm right, but my Fourier transform sense is tingling.
Yes. So this is like, let's say these are tuning forks that are like the size of a fork, right? These tuning forks can fit in your hand. These tuning forks can fit in a car. These tuning forks are like the size of a chair. I don't know. So these tuning forks are massive. These tuning forks are tiny. So if you play a very loud sound that's kind of at this small frequency, it will make all of them start resonating, even though they might be slightly different sizes. Like one might fit in your hand, one might be a bit bigger, one might be a bit smaller. But it's never going to make these ones that are the size of a car resonate because they're just so far off. Yeah?
Mm-hmm.
So we do a pulse, which is at some kind of frequency, and everything near that frequency will get excited. But it's a very small range when you look at the whole scale of like all possible nuclei. So you have to tune to each nucleus. Does this make sense so far?
I think so, yeah.
And so when we do NMR, we get what we call an FID, which is so the raw data we get is a graph with time here. And say we do one pulse, we get a graph that looks like this.
That does make sense.
Yeah.
Yeah.
And when we Fourier transform this, we get a graph which looks like this or whatever.
Yeah.
So the frequencies within here get Fourier transformed and will give you frequency points on here. Does this make sense?
It does.
Okay, good. This is Fourier transform NMR, which is most NMR. And so everything I've explained to you is the most simple possible pulse sequence.
I mean, I don't have to say. Okay.
Yeah.
It does feel simple.
Mm-hmm.
It, like, yeah, the thought process behind it was spin. Yes. But looking back on it, so far it does feel relatively simple.
Yeah. For me, the hardest part was this thing.
Yeah, I mean, I imagine without the in between.
Because I couldn't find this explanation anywhere.
Yeah, I mean, I imagine without the in between, even with the expression was a magic trick for me. So without it, I can only imagine.
Yeah. So this is when I say pulse sequence, we tend to draw diagrams that are like this, and this is time, and this is our radio frequency pulse. Oh, I will say when we say radio frequency because all of these frequencies are within the radio frequency range, as in megahertz. Is megahertz radio frequencies?
It should be. If I'm not mistaken, RFID cards will operate on megahertz.
300 kilohertz to 300 gigahertz. That means megahertz is in between. Yeah. Okay, so these are all in the radio frequency range. And when we apply our pulse, we're basically saying that we do nothing and then we apply this 90-degree pulse for a certain amount of time. And then we do nothing. And what we get then is our signal like this. Yeah? Mm-hmm. Now, you've seen the spin echo thing.
I genuinely opened it right now because I sensed it.
Where we do this, and then we do this, and then we get some kind of signal, which looks like this. And this time...
Oh my goodness, it makes sense!
And this time, match.
It makes sense! Because applying the field rotates it.
Yes!
Wow!
So the only thing in this picture is that in this video, you see the vectors fanning out, and you don't know what does that yet.
Okay, but if you would it, okay, so recap once again, make sure I understand. If you basically have this nucleus, and then if you apply on it a magnetic field with that with the llama resonates with the llama frequency, then
Yeah.
You can think about it as how long you apply that field for is how much you rotate the magnetization.
Yes.
That's
Because
actually
it's how long
really
you're
cool.
applying the B1 field.
That's actually really cool.
Yeah. So,
I'm looking at the echo one that stretches time now to see if I can, because it shrinks. Okay, hold on. Let me look at it because this is so far so good. And then
okay, this I'll explain after. This is the thing we'll get to.
okay,
Because I think this diagram is horrible without context. Like this video doesn't make any sense because they're like changing what they're doing halfway through the video.
I know that's the one that made me genuinely terrified of the topic. It's possibly, I don't want to say definitively, because let's give them some credit. It's possibly the worst visualization I've ever seen. But okay.
So
yeah.
So when we have our, let's go back up to this corner because this is where we did it. Can I just select all this and delete our spirals? Okay, we have our magnetization vector. So it's like this, and it's processing around in the XY plane. Yeah. Basically, if we now look at individual nuclei again, every nucleus is processing at a very slightly different speed, just because of differences in the local field around our sample.
Yeah.
So this might be due to electrons or magnetism in your sample, or it can just be that the field in the machine isn't perfect. But essentially, there is some difference in the speed of precession of these of each nucleus. And so what this means is that if we ignore the Z component for now, so we're ignoring this kind of relaxation back to Z, what this means is over time, our vector will kind of just get smaller. So it will get smaller, and it will get smaller, and eventually it just goes to 0. And this is because we start with them all like this, but then over time they start to fan out, and they fan out even more, and even more, and even more, until they're in every direction in the XY plane. Therefore, they all cancel out to 0. Does this make sense? So this is a type of relaxation.
I think so, but hold on, that's for the nuclei or nucleus?
This is like the sum of them all is 0, but one individual nucleus will still be pointing in one direction. It's just that
in that case,
because they all
yeah, no, for a second I was confused because I heard it was multiple ones per.
Okay.
But no, in that case that makes sense.
So in the rotating frame, most of them, like one that's spinning perfectly at the llama frequency will stay in this direction, but one that's spinning slightly slower will start going that way a bit and drifting, and one that's spinning slightly faster will start going that way and drifting, until eventually they're just in every direction, right? And in the stationary frame, all this would look like is that this is spinning at some speed, and the others slowly like start to break out, and they're spinning at slightly different speeds. And you can imagine this, right?
Yeah.
So this is what we call T2 relaxation. I'll say T1 relaxation you've already worked out, and that's this returning to the Z axis. So T1 relaxation is this thing that the timescale varies massively. It can be like microseconds, or it can be days. T2 relaxation is this thing, and it's a dephasing really of the nuclei.
It's going to be relatively fast, isn't it?
I actually, how fast is it? I think it's quite fast. Yeah, I think it's in
because
microseconds usually.
it should be per rotation.
Yeah, it does vary as well per sample and all that. Now,
Doesn't
yeah,
T1... Wait, hold on. This was T1 and T2 or T0 and T1? My brain...
T1 and T2.
Okay, T1 and T2. Doesn't T2 function just as really unhelpful and awfully annoying noise?
It doesn't actually function as noise. It just reduces your signal.
Oh.
Like your signal just
okay.
disappears.
In that
because this vector just gets smaller and smaller, right?
Okay, in that case, doesn't T2 function as really annoying reduction in the signal?
Yes.
Oh, okay, good. Because I'm thinking like if this one happens over the course, well, okay, never mind. This one happening on the course of the day doesn't really matter. But if it does like kill, yeah. So even if even if T1 was happening over the course of a day, it won't matter because after a second it will already be nullified. The signal will be reduced.
Yeah. Whichever one of them is quicker will make your signal go to 0 first.
That makes sense.
So like if T1 is quick, then T2, like it doesn't matter if your T2 is long because if either of them relaxes completely, then you have 0 signal.
Yeah, that makes sense.
However, there is a trick we can do that harnesses the T2, and we're essentially using the T2 against itself. And this is the spin echo pulse. So if let's say we have them like this and they start dephasing or whatever, and then we apply a 180-degree pulse. And so when I say a 180-degree pulse, do you know what I mean?
Twice as long, the same oscillation but twice as long.
Yeah. So we apply the B1, and it's twice as long. So all of these flip 180 degrees in the ZY plane. Yeah.
Mm-hmm.
Now
they're going the opposite way.
Yeah. So now they're all like this. I just
so basically,
my third axis.
Okay, so basically, I don't know if I'm sure when it was but like, so basically, if this is the point where we do the 180, right, in the middle, then
yeah,
and these two are the same exact unit of time, some kind of delta t, then right here they would have already traveled. They would have already spanned out some kind of q distance. Then actually no, right here they start at 0. Then they would have spanned out some kind of q distance, and then they would go back to 0.
Yes.
So you basically can you keep doing this? Just
you can, but there are kind of extra effects that will make them.
I imagine, of course.
Eventually, they disappear.
Yeah,
but yeah, you can keep doing this, and we had a pulse sequence that we were using today, which basically just keeps doing the echoes like over and over again.
Hilarious.
We just spam it.
It's just comical.
And so the main point of this isn't actually to like fight against T2. It's more to overcome a problem with the instrument, which is that let's go down here. So we have this, and we excite everything with a very, very fat field pulse. So radio frequency pulse.
Mm-hmm. This
is a very strong pulse, right? Mm-hmm. And then immediately after, so this is our 90-degree pulse. So this whole thing is 90 degrees. And immediately after, we get signal. Yep.
Yeah.
The problem is that this pulse doesn't perfectly stop after this amount of time. Some of it kind of bleeds through a bit and goes past that time.
And the 180
and so it kind of screws with our FID. Like some of our signal ends up being from the pulse itself, because this is massive. Like this is actually huge. Yeah. And our signal is really small in comparison.
Okay.
So any bleeding of this is still quite big compared to our signal.
Hold on, if we do a timeline, right, from the beginning to the end, then right here we would have the 90-degree pulse. and let's say right here we would have the 180. Then if I'm understanding this correctly, this would be some kind of delta, and this would be double delta. Before we get the same amount of T2, before we get the same amount of T2. Because right here is going from 0 to some amount of spreadiness, but right here is going from spreadiness to 0 to negative spreadiness.
Why do we need negative spreadiness?
Well, no, it's not we need negative spreadiness, only that, like, we don't care about the direction in which they spread, we just care about how much they spread, right?
Yeah.
So in this case, we have effectively reached the same amount of spread, so the same amount of disappearance, but we did that in twice the time. So
yeah.
So we had twice as much time to let this massive thing just blow over.
Yeah, but so this spreadiness section doesn't matter because what we measure is when they're at 0, right?
Yeah, so
because 0 is when they're aligned, and so we get an actual signal.
Yeah, so
because when they're all spread perfectly, there's 0 signal.
So the graph would be like this, and the 0 would be, well, actually no, it wouldn't be like this because that would be the end. But it would spill over a bit. It would over a bit, and we want to measure it right here and right here. And so right here there's still spillover, but right here there isn't anymore because we had more.
What is this wiggle here? What is that?
That's the 180 pulse. It's meant to be bigger, but like.
Okay. Yes, yeah, you're correct. So the point is that instead of doing direct excitation and measuring
really
our
clever.
FID immediately after the pulse, we now can measure it some duration of time after our last pulse.
That is really clever.
So we get no kind of interference from our instrument. So this is a spin echo or a Hahn echo.
My goodness, that is genuinely so clever, this entire thing.
And this is like the second most complicated pulse sequence. And I'm going to be honest, I don't really understand any other pulse sequences. There is a thing about phase cycling, which I think we'll talk about another time. But basically, it's that if we go back up here, phase cycling basically means that when we do this experiment, we repeat this like hundreds of times and like millions of times or whatever, as many times as you can in a certain time frame. It's this whole experiment.
Yeah.
Because each FID is very small signal, right? Like we get barely any signal, and it's very noisy. So we have to add up a bunch of experiments, and adding them up, the number of experiments you can do depends on our T1 and our T2. Yeah.
Mm-hmm.
Because if our T1 is like 5 seconds, then if we try and pulse them too quick, they don't have enough time to relax. And so what happens is, say you tip this way, and you record it, and it relaxes like this way. Then if we apply another 90-degree pulse, it goes here, right?
Yeah.
So now it's in the wrong place, and so we get less signal because it's closer to the z-axis. And so we want it to be back to the z-axis when we pulse.
It's kind of like
ideally
something overheating, except instead of heat you have.
Yeah. When we repeat a bunch of experiments, but part of what we do is we cycle the phase, which means essentially it means we apply B1 in this direction, and then the next experiment we apply it in this direction, and then we apply it in this direction, then we apply it in this direction, and we do all 4 directions of B1. Can you work out how we apply B1 in different directions?
It's not going to be just moving the coil around, is it?
No.
Just twisty, that would be too easy.
It is easy, but it's not that.
Do you rotate the sample?
No.
Ah, damn it. Once again, it would be too easy.
I think the key is in what I called it, which is phase cycling.
I Oh, I have a headache.
Me too, actually. We should stop soon.
I had another question about, like, can you not also just rotate it completely? It's just apply B first, or is it that you don't know exactly where the arrow is, and so it's better just.
I actually don't know the point of phase cycling yet.
Is there?
I'm just bringing this up as another trick you can do with B1.
Is there another coil?
No. That's what I thought initially. I was like, how the hell can you just make this go in multiple axes? There's not another coil. It's actually really simple.
I've already said 3 things. All of them were wrong.
Okay, well, when I say phase, what does phase mean?
Well, phase is the offset of a wave.
Yes.
But like, if you offset this, do you genuinely wait? But the offsetting that way doesn't make sense to me.
It does. If you offset this, then say we start here instead of here. Now our blue arrow starts pointing up and stays pointing up. Okay, that's literally it. That's the whole thing. I got
used to it, but I still absolutely hate the rotations. The amount of rotations. I hate it. It's awful.
We started hating spin, and now we hate spinning.
No, it's not even the rotation. It's just how many rotations are happening at the same time.
Yeah.
It is headache-inducing. Well, I mean, it makes sense. It doesn't.
This is gonna look so good in an animation, though.
The entire time I was thinking, I didn't want to mention it because, well, now you've mentioned it, so I can. But in Blender, there are the nodes for rotating vectors are absolutely phenomenal, and I could just simulate this. So I'm just thrilled to see what it will look like. Okay, so that makes sense. So you do it in order to reset. So you can like reset the sample.
I actually don't know what the phase cycling is for. It's to do. I think it's because when we Fourier transform and it's out of phase, we get some peaks can be like negative or like half negative, like this or something. So the phase cycling means that you measure all possible phases, and then what we actually do every time we have an NMR spectrum, we manually phase it. So we manually kind of drag this number, and we cycle through. So it might start looking like this or looking like this or whatever, and we cycle through until it looks like this. So I think the point of the phase cycling is just that we sample every possible phase. And then when we actually look at the spectrum, we can then just change the phase that the Fourier transform uses.
Yeah, it does.
So I think the point is that our FID could start here and go down, or it could start here and go up, or it could start like halfway and go a bit down, then up, and then, you know. So the point is to get our FID like standard, I think.
That does make sense, yeah.
Yeah. So when we do NMR, in terms of like what I actually do in the lab, for one, I might take out the probe, put a sample in, I might switch probes or whatever. We then choose which nucleus we want to measure, and we tune to that nucleus. So we know what the frequency is, and we tell the machine to pulse at that frequency, or tell the probe to pulse at that frequency. And then we have to tune the coil, the red coil, to receive that frequency. And so this is basically you twist a knob. I don't actually know what it does inside, but it does something that makes the coil receptive to that frequency, so it will absorb it. And if you don't, then it like doesn't absorb the frequency, and you end up like frying your probe. The way I broke our probe, which is now fixed, was I was just tuning it too fast, and I twisted the knob too fast, and something clicked inside. That was literally it.
The crunch I mentioned earlier. Yeah.
Yeah. Yeah, literally, yeah. I didn't like fry the coil or anything. I think it's just the tuning mechanism had some like resistance on it, and I bypassed that resistance. But yeah, they fixed it now. So first thing we do is we tune to the nucleus we want to measure. Then what we do is we choose which experiment we want to do. So the most simple one is our direct excitation, which is single 90-degree pulse. Yeah. Which has it still gives you a good a good measurement, but you might get this bleeding of the pulse in your signal. And so the second most simple one is this echo, which is a 90-degree and then a 180-degree pulse, which will give you your signal without the bleeding of the pulse.
Mm-hmm.
So we put our sample in, we tune, and we say which pulse sequence to do, and then we hit run. And what it will do is it will just repeat this pulse sequence over and over again. And we have to set the delay time between pulse sequences. So if we know that our sample has a T1 of like 3 seconds, then we might set the pulse sequence to like 5 seconds. Or we might set it to 10 seconds so it's fully relaxed. So the T1 isn't like how long it takes for all of it to relax.
Do you have a way to reset a sample?
What do you mean by reset?
Well, to have it go back to just the magnetization being on the z-axis.
There is a technique. It's another pulse sequence called. It's either saturation or desaturation.
270.
It's not 270. It's actually you just apply successive 90s. Is this? I'm thinking of desaturation actually. Okay, I know a sequence that will make your signal go to 0.
Yeah, that makes sense.
Which is you apply successive 90s over and over and over again really fast, and you essentially end up with all your magnetization vectors on a sphere. So the net is 0. So this gets rid of even the Z component. In terms of resetting it to vertical, I don't think there is an easy way to do that.
Because like if you have something with a T1 of even like 6 hours.
Yeah.
Do you need just like multiple samples of that thing? You run the first one, then after it's done, you just switch it out for the second one. Because you can't wait for T1.
Honestly, no one measures things that have a T1 that's that long. So generally, most samples, the T1 is like a few milliseconds or whatever.
In my head, I genuinely imagine it like just cooling. Just like you need to, you have just like you sometimes can overheat things, but you can't cool them, so you just swap them out for a new one.
There have been times when the person supervising me, so like postdoc or professor, where we've been doing a sample with a long T1, so maybe like a couple minutes, and we accidentally run the wrong spectrum.
Oh.
And then one of them goes, "Fuck! I just wasted the magnetization." Now we have to wait 5 minutes for it to relax. So it's like so for them it's like very satisfying when you get to start it fresh with full magnetization.
And this is absolutely and definitely not wizards doing a spell and waiting for their mana to recharge. It's not.
Yeah, they're definitely not. No, it's not. It's not mana
science.
recharge. There's just a cooldown on how long it takes to get your magnets.
I really need to make a stop doing NMR meme.
I was thinking about this. I was thinking about making an NMR actually. This is real NMR done by real physical chemists.
They have played us for absolute fools. Hello?
Yes, I would like llama frequency, please. I would like B1 of it.
Spins weren't meant to spin. But I mean, okay, I have to say, your explanation was brilliant of this.
Good, I'm glad. I felt like I didn't know what I was doing for half of it, and it kind of came together.
Top left corner, I can relate to that feeling. the thing in the top left corner, I could just feel how painful it was to research all of this without that explanation.
God. Yeah.
I could just feel it.
But like, all the books were like, oh yeah, this just produces a constant field in the rotating frame, and I'm like, what? Where does it come from? Is it not spinning in the rotating frame? Like, it just didn't make any sense to me. I did a drawing. Where can I draw this? I'll draw it like down here. I did this whole drawing in my book where I was like drawing. So I started with the green arrows or whatever, and then I switched to the rotating frame, and drew them all in the rotating frame. And I was like, how does this make the continuous field? Because it was like, you know, you start like that, and then back, and then and it. I went into the rotating frame, and I was like, okay, it does that, and then it does that, and then it does that, and then it does that. and it just didn't make any sense to me. I was like, how does this make a continuous field? So yeah, it was very painful, but I got there.
It is really impressive.
It was just a book I found, eventually explained it. Like, it used this diagram. It didn't draw it the way I drew it, but it showed the 2 arrows. I just like drawing time steps because it's basically animation. I'm just gonna go for a minute because I really need the toilet.
Yeah, sure.
Right back.
Oh jeez, it's been 2 hours. You know what? If I might as well indulge. Simulation, and then what we'll do is mesh line. We're gonna start at 0, and then we're gonna plug it in here. Extrude mesh, right. Offset position, selection, we're gonna start at 1, sound location 1, this doesn't matter, then mesh to curve right here, curve to mesh, circle, this, then offset, let's do that. Why did nothing happen? Oh no. Okay, if I just plug this in right here, it doesn't. No, it does not either. Oh yeah, because 1, that makes sense. Wait. Like no, it's. Oh, because you need to select the top, right?
Hello.
Hi.
Are you drawing it?
I'm trying to simulate it, but I'm really struggling. Oh. This is splendid. Okay, that works. So
I think this has been a productive day.
Yeah, I honestly understood way more than I thought I would. Because I just feel like I for some reason need to put it in the geometry notes. I cannot.
I would love to see everything animated.
Okay.
Because it would be better than the Wikipedia page as well.
So, I just feel like it would be really, really easy. I don't know if I'm.
I agree.
I don't know if I am just completely not being able to finish a thought, but completely not being able to conceptualize what it will actually take to do it. But let's see. Arrow from 0 to the end line, drawn geometry. Oh, this gives us an arrow. And then let me just have it rotate. So rotate vector. I love that in Blender there's vector rotate and rotate vector, which are two generally different.
I mean, vector rotate probably means rotate along a vector.
Yeah.
Or using a vector.
That's the difference. You either vector rotate, so you rotate using 3 vectors and an angle, or you rotate a vector. I just find it always hilarious. Okay, so this goes to position. This goes. No wait, this goes in here, then goes to position, then goes out, and X, Y, Z. Let's not do Z, let's do Y, and let's have the angle be something slight. Oh, I am good at what I do. You can see where I'm going.
I would love to have an animation that has everything with the stationary frame on one side and the rotating frame on the other side.
Yeah, well, okay, the rotational frame will be a bit more annoying, but with the pulse, let's try a pulse. I just first need to see it. So we're gonna have it rotate around the Z axis. Wait, hold on. What kind of
the Z-axis is our massive magnet field.
Okay, so
our B0.
Okay. Around what axis is it rotating? When the pulse happens, it's rotating around the X, correct?
Yeah. I want to check actually if there's a convention if we say B1 is an X or Y.
Just 100s.
Yeah, I think we do say X.
Oh, that's curious. Why is it shrinking? Like, I've already made a thing where I can just enable pulse. I can disable the pulse. Oh, that's why it's shrinking. I'm an idiot. Yeah, that's why it's shrinking. That makes sense. It's too good to be true. A T1 decay. T1. Wait, is it decay? It's
relaxation.
Relaxation. Okay. Oh, jeez, yeah, because it's chemistry, so it's relaxation. If it was physics, it would be decay.
Well, it relaxes.
There's an equally valid argument.
It also decays, but it relaxes.
I mean... I'm trying to do it in a clever way.
My girlfriend just told me she's been watching the whole stream, and now
I am so sorry.
suddenly I'm like way more critical of everything I said.
I I am so
standards have gone up.
Oh, I am so sorry. It always messes with me when someone says when anyone says they're watching the stream, because I sometimes forget. I sometimes forget that this is live.
She's in the chat. Wow.
Oh, Zoid, it's you. Oh yeah, Zoid was here before. That's true.
Jubians. She's a number 3 top fan.
She said
somehow I'm number 10. How do you get XP?
Oh, Flame, you're breaking my heart.
Yeah, she's just tuning into every stream. I'm only tuning into the ones I'm speaking in. I'm just tuning to Nuclei.
XP is really dumb on YouTube. Don't tell YouTube I said that.
Rolled and smoked, true.
Number 2 already. Wow.
Wow, she's how's she doing that? Oh my god. She's cracked at everything, I'm telling you.
Well, at least she's not number 1. I was setting up for the comical timing of. Oh, never mind. Swing and a miss.
Yeah,
I was going for the comical.
Yeah, it would have been funny.
But you can see the vision, right? Of like.
Yes.
This is what I imagine. Zoid, I hope this wasn't disappointing. Why is it stopping? Well, because I'm turning it on and off. This will be like the pulse.
Oh, okay. I was like, that's a weird angle to be going to.
Yeah, because that's a nice thing. I'll be able to simulate this, not just animate. We could just disable the pulse whenever we want to. So another thing would be
You'll be varying the pulse length.
Yes, look at me. I'm a scientist. Let's have something tiny. Actually, no, random. I can do multiple at the same time. I can. 0.01 and then minus 0.01. This is my hyperfixation. This is genuinely my hyperfixation.
Did you just call my PhD your hyperfixation?
I mean, in a way, yeah.
Yeah, fair enough. It's my hyperfixation as well.
No, in this case, it's just like when you were describing it, I was genuinely the entire time I had this in the back of my head and I couldn't get it out because it was just. I mean, you're seeing what I'm seeing. Wait, repeat. Okay, let's like 10 of these arrows. 10 of these bad boys. Join and join. Go in there. That did not work in the slightest. Oh, because of the red connection, right? If I take this off. Work. That's lovely. Now can I plug this in as the ID? This in right here. The answer does appear to be no. Okay, you know what? No, it's I am. Whoops,
I sent you a GIF.
You've sent me. This is just. Wait, hold on. Actually, Oh wait, hold on.
Are you thinking the other one?
Yeah. I can finally understand what it means. I finally.
Actually, you don't know this pulse sequence yet.
Saturated.
This is how we measure T1.
Okay, considering how consistently giving 90s was desaturation. Or was it saturation?
I'm thinking. I think it is saturation when we do consistent 90s. Yeah.
Okay, so is saturation the same as saturation recovery? Is it the same cut? Is it the same?
It uses saturation, yeah.
Okay, so when T1 measure, this is content, folks. We have a
I need to
genuine.
send you that. My girlfriend just sent me. It's loading. Hang on, I've got really bad upload speed on this Wi-Fi. It's 1 megabyte. It's taking 5 seconds.
Oh god, that's what you had me with. That's not fair. That's one of my favorite memes. It's not fair.
We need to make a relaxation one that shows the like spiraling back to the z-axis.
In the video that I will include, the mandatory Pukeko video. Eventually, there might be a position where serious people will start actually looking into my channel, for reasons I cannot disclose publicly just yet. But I like the idea that they would randomly click on the live stream and then just see, well, this frame that you're seeing right here. I am curious what they would think.
Yeah.
The T1 measurement uses saturation recovery process. Every single time I see it, I just see the Grinch.
Oh yeah, we do sometimes you do inversion recovery and sometimes you do saturation recovery, measuring T1s.
Okay, but saturation is the 90s.
Yeah, we apply a bunch of 90s and our magnetization vectors end up spread over a sphere.
What is that used for? Because it feels just like.
What is used for is let me go back to the whiteboard. We really don't have much space left. I'll go bottom right of the screen. So we end up with all of our spins in all directions in a sphere, right? This is kind of the same as saying both levels are equally populated. Yeah.
Yeah.
We're gonna skip over what it means to translate a vector into quantum energy level model because I have no idea. But once we've done this, our sample is still in a fat magnetic field, right? Like it's still in this massive magnet that's like 5 meters tall. So if over time, they will eventually end up all pointing upwards, meaning not all pointing upwards, sorry, mostly that our net vector will end up pointing upwards, meaning this level is slightly more populated than this level. Yeah?
Yeah, but what is the difference between them being spread out over a sphere versus them being spread out over a circle? So we know.
The point is that when you spread them out over a sphere, everything becomes independent of T2.
And how does that help?
Because we want to measure T1. And if we want to measure T1 and our T2 is on like a comparable timescale, then that becomes an issue.
Oh, okay. Wait, why is it become independent of T2?
Which way are you drawing this circle?
XY.
XY or ZY?
XY.
XY.
Because this is the circle along which.
Okay,
like,
yeah,
the
you're right. Yeah, if you had
would
them
be on.
all in a circle in the XY plane, you're right that it wouldn't actually make a difference. But you can't really get them. On.
I suppose in that case it would be. First of all, I don't know. I instinctively drew like it as an arrow, which it wasn't meant to be. Pure instinct.
I'm just thinking. I mean, it wouldn't make a difference if these are all like spread out in all directions on the XY plane. It wouldn't make a difference, but I think you just can't get them to do that.
Yeah, okay. I mean, that makes sense, but
like it's just a lot easier to apply a bunch of 90s and
yeah.
you get
Could you
this
describe the T2 to me again?
The T2 is the dephasing as they process at very slightly different speeds.
Yes, but it reduces the signal, and that's the part that confuses me. How does it reduce?
It reduces the signal because let's say they're all pointing this way.
Mm-hmm.
We have big signal. Now let's say some are pointing this way, some are pointing this way, some are pointing this way, and they fan out. Our net vector is now no longer this long. Our net vector is now this long.
That confuses me because why would it be shorter?
Because you're adding up all the vectors.
Yeah, but I mean, all the vectors are still on average pointing in. Like, all the vectors are pointing in that direction. Wouldn't they need to be pointing somewhere beyond this line in order for it to become shorter? Like, if you add this...
No, because if it, let's say you have a vector.
Wait, are you adding them or are you averaging them?
Yes. You are. I think it's the same effect either way. Yeah, well, you are adding them, but it's the same as averaging them. Well, I mean, so let's say you have, if you have a vector that points this way, versus a vector that points this way, a vector that points this way. The vertical component of this vector is this long, whereas the vertical component of this vector is this long, right?
Yeah.
And if you have the same number of these, so let's say we have 10 of them pointing this way versus 1 pointing this way and 2 pointing this way and so on up to like 10, right? Now, the sum of all these 10 is 10 times this length, whereas the sum of all these 10 is maybe like here, but it's a lot shorter. Yeah?
Okay, that makes sense.
Yeah. Okay. And as these go all the way in a perfect circle, like spread all around, it goes to 0.
But by saying like, do we average them or do we add them? I don't think it matters. Frame, I've got bad news for you. I think you're a physicist.
It doesn't matter because it's. I mean, yeah, you are adding them because if you were averaging them, then you would only get the size of one vector as your final answer, which is very small.
Okay, then that doesn't.
Because then your magnitude is 1 spin.
Yeah. Okay. Wait, but
which
hold
is
on.
A very small amount.
Hold on. There's another thing I'm confused on because this you say that this means that like T2 doesn't affect anything anymore.
Yeah.
But isn't the whole problem of T2 the sum shrinking?
Ooh, question. Dude, that's a good point. You've actually caught me out here.
Because this feels like this feels like, you know, oh no, my house is on fire, so you just exploded, you know.
This is a good question actually. That you've spotted something I didn't realize. So I think there's a problem in my understanding of this. Okay. I know. Okay, so saturation recovery. I'm going to remove all this. So first we saturate, and this is a bunch of 90s. So we saturate our magnetization, and we end up in every direction on a sphere. Then what we do is we wait for a certain amount of time, so we will end up with some vector pointing up. Yeah.
Mm-hmm.
Then what we do is we do a normal 90-degree pulse and a normal NMR experiment. So we pulse this, it goes here, and it spins and whatever, and we measure this, and it relaxes back to vertical. Yeah?
Yeah.
This part is a normal experiment. this part is dependent on T1. I mean, this is also dependent on T1, but it doesn't matter. As long as we do this the same every time, what we can do is we can vary the time between this and this. And so if we give it like no time, then this vector is very small. And if we give it loads of time, then this vector is massive. It's as big as it can be.
Yeah, makes sense because they're all coming together to the...
Yeah. So what we do is we repeat this experiment at different time lengths for this. So we vary this length per experiment, and we plot how big is this signal based on this length. Does this make sense?
Yes, it does.
So you end up with a graph that's like
T1.
here, here.
Yeah, so in that case, that tells you the T1, because you know...
Yes. It tells you how long it takes for the relaxation to go from this sphere to perfectly vertical.
That does make a lot of sense.
Yeah. You caught me out because I forgot this whole section, and you were talking about this, and I was like, it doesn't depend on T2. And then you were like, well, how do we measure it? And I was like, but then I remembered we just do a normal experiment.
See, we did, at the very beginning, you did mention, like, oh yeah, this is all about you making me look like a fool and me making you look like a fool. But I haven't asked a single question that actually stumped you the entire stream. This is very one-sided. I don't like this.
You haven't... I think I've felt stumped a few times, and I just recovered.
It's not fair.
You saturated me, and I recovered.
Oh, you flirt.
Yeah. There is also inversion recovery, which I think is... We do a 180 pulse first, and then do something. I can't remember how it works. It's slightly better than saturation recovery, I think. But I don't know that pulse sequence yet. But yeah, so all these different pulse sequences are different NMR experiments where we're just flipping the arrows around whichever way we want, and it tells us different things. I have a GIF. Where's... Is this? We're just doing this. But with arrows, right? We're just flipping magnetization in a bunch of directions.
A master of chemistry, ladies and gentlemen. I have a GIF for this. When you're a doctor, I want you to still be like this. Don't change. Eventually, you as a professor, you have to be like, students ask you a question.
I will be putting GIFs in my slides.
Yeah, every other slide is a Pokeko. Actually, that would make for a banger presentation. Every slide, instead of the title, is just the bird.
Okay, I think I've NMR'd myself out today.
Yeah.
Are there any like key questions you have?
I genuinely understand it. It's not even that
I think one big question you should have is, how does this relate to molecules?
I completely skipped over that because my brain is just so... For now, I knew nothing.
For now, it's physics to you.
No,
yes.
for now, I knew nothing about NMR. So for now, I'm just dealing with the process, not anything related. In a vacuum. As I mentioned, I've been hanging out with Remco too much. I'm still in the mindset of theoretical physics, and the question of why we're doing this is like... what do you mean why we're doing this? We can. Good enough.
Yep.
But really often I have this thing when you explain stuff to me where I don't have any questions because I just don't understand something well enough to even have a question. And I've had this about NMR. That's on the beginning of the stream. That's why I didn't even know where we begin because But this time
you didn't know what to ask because you didn't have a starting.
Yeah, but right now I do understand it and I don't have any questions.
Good.
Very
Yeah,
disappointing.
I guess next time we'll talk about how it relates to molecules.
Yes.
It's basically stuff about if you zoom in on this part, this here, it's quite literally just that more electrons around your nucleus will make it react to the field slightly more or slightly less, and so this frequency changes a bit. But that's basically it in terms of frequencies. And so in undergraduate chemistry, we don't get taught anything on this whole page. We get taught this. That's it. We get taught that. We don't even get taught tuning. They just tell us this. They might say that the range is different. They make us memorize like where the different like it is a carbonyl here or is a methyl here, and it's like they make you memorize where the frequencies for certain common parts of molecules are, which I hated. I was like, wow, NMR sucks because I don't like this. And I didn't zoom out and see all of this.
I mean, I can see how. Well, no, no way. You mean to tell me that like undergraduate chemistry ignores all the interesting bits and just focuses on the memorization? There must be a first time for everything.
It's almost like they don't like physics.
There must be a first time for everything. Terrible. We do have to end it somewhere because otherwise we won't ever end. But this was
I think we should end it here.
This was a treat. Should we end it in any special or just casual? Because we're hilarious. Well, I guess that's it then.
It's still live. It's still live for me. Oh, is it?